Hello, welcome back to another operating systems lecture. So so we're just building up from the stuff we did last time really. If you remember, in the last lecture I looked at loading data from the disk. You remember that we've been writing boot sectors, a few different boot sectors now, just to figure out how to write low-level code and how the computer works. And so in the last lecture I loaded some extra data from the disk additional to the boot sector, and we sort of got to the stage now where we've been writing assembly code, looking at how the computer boots, learning a bit more about the computer, and what we want to do in the next lecture after this one is to be able to write a kernel in C. And when I say write a kernel I mean just a very minimal piece of C code, just to demonstrate how we can bootstrap from having no software support on the computer other than BIOS, which is like a very low level support library for us, and to having C code running, some code that we've compiled in C. And then once we have C code we can start to appreciate how C is actually a high level language. Often now we think of it as a low level language when we look at things like Python and Java and all of those things. But we're going to learn to appreciate C a bit more than we probably do. Okay, so what we're going to do now, this lecture is probably, it might be the trickiest one maybe in terms of information overload. It's not so complicated what we're going to do, but it's more a case of there's a lot of stuff to read about and to understand before you get your head around it, and I'm just going to really try and give an overview of this thing that we're doing, which is switching our computer into protected mode. So I mentioned before that when our computer boots, it boots in like a legacy compatibility mode, a 16-bit real mode, which is backward compatible with the earliest 86 chips. And it means that even on my 64-bit laptop, I can boot like Windows 95 on it, and the software, because the software doesn't know because Windows 95 doesn't know anything other than a 16-bit computer, it will never make the switch into 32-bit protected mode that my CPU can offer, or 64-bit mode in my case. So we're going to look now at how we can switch out of this limited legacy compatibility mode into 32-bit protected mode. I'm going to do that because rather than switching to 64-bit mode, you can have a look at how to do that yourself. What you find though is that a 64-bit architecture, an 86-64 architecture, is really just an extension of the 32-bit mode. So the way it's structured is very similar. The kind of structure the CPU uses, the state that it has, the memory protection is very similar, but you get extended registers to 64 bits rather than 32. Anyway, you can look up all that stuff and I'll point you in the right direction. So I'm just going to get on with this really. I'm just going to, rather than writing everything out now, I'm going to build up the example of switching to 32-bit mode and just talk about things that I'm doing, and then you can look at the code later and try and figure out how it all works. But really once we've done this, what we should have, the goal of this lecture, is by the end of it we'll have a low-level function that allows us to switch into 32-bit protected mode on the CPU, and then once we're in 32-bit protected mode we can load a 32-bit C compiled kernel. So firstly, why do we want to switch into 32-bit protected mode? Well, the whole way that CPUs have developed since the early operating systems, and by early I'm not talking way old, I'm talking like Windows 95 and similar 16-bit operating systems. What was found with those is that often you write a piece of code and it would crash the whole system. And one of the main reasons it did that was because there was no protection between processors. So my operating system might be running some code, like doing some driver code routines, and I might write a process, to some database application or something like that. And if I incorrectly reference a pointer or something and access the wrong piece of memory, then because there's no protection at that real 16-bit real mode, then I can quite easily corrupt memory of other processors and cause them to crash. and in the worst case I'll hit something like the kernel code and cause the kernel to crash. So that's why we often get crashes with those older operating systems, so they're not so stable. So protected mode is a CPU feature that all modern CPUs have now. They've had it for quite a while actually, but they've kind of stuck with it. And you can sort of segment memory so that you can protect one piece of memory from another piece of memory. So code running in one section of memory or one segment of memory, if it tries to access code in another segment outside, you can imagine it like being fenced in, then it will cause an exception in the CPU. And you can also have privilege levels so that you can have the kernel code running at a higher privilege level, which is the ring level. And that means that the kernel code can access any memory, but a user process, like my Office or whatever whatever applications I'm using on a desktop, they have a lower privilege level usually, and they can't directly access memory in the kernel. So this is why it's important, because without this we wouldn't have the stability. There's lots of other things with the architecture that have been improved in the protected mode to do with paging and things like that, so managing memory more efficiently. So things like execution protection, which is quite important now. So sometimes if somebody is corrupting memory to try and, in a malicious way, to try and break into a machine, you can now have the hardware enable certain memory regions as non-executable. So even if there is some memory corruption in there, it will be more difficult to execute malicious code injected into memory. So there's lots of things like that, and that's why people don't write 16-bit real mode operating systems anymore. At least not for general public use. Right, anyway, let's get on. So I'm just going to build up these examples. So what I need to do is go to my code. So what this means so far is that all the code we've done so far is in 16-bit assembly, using 16-bit opcodes on the CPU. But now we're going to switch our CPU into an enhanced mode, and then we can make more use of it, of all the features it has. And I'll just reference this manual too. So if you're wondering where all the information is about the CPU, then if you go onto the internet, you can download from Intel. You can get their super large, how many pages this has got? It's got like 3,000, nearly 3,010 pages, and this is the manual for low-level development and control of the CPU for the 64-bit and 32-bit 86 architectures. So you can have a look through that. I'll reference some particular bits of it probably during this, but you'll see there's lots of stuff in there, and it explains exactly how the CPU works, and all the information that you'll need is in there. And so if you want to go and look at that at some point, then go ahead. And so this will tell you how you can switch modes into enhanced mode, and how the interrupts dispatching works in protected mode, in 64-bit mode. All of that stuff is in here. Right. So, right, let's get on. So here's my boot sector. So I'm starting with something similar to what I had before. So I've set up my stack just out of the way so that I don't clobber it with my code. There's no risk here because I'm not loading any extra data here, but I will do in the next lecture. And all I'm doing here is, remember I made a print string function, and I'm calling that print string function on here, and it's going to print out this message to say that we're in 16-bit mode. Remember, there's not much feedback we can get at this low level other than printing messages out. So that's what I'm doing to let me know what's happening. Now when I've done all of this, I should land in protected mode and print a message out. So how does this work then? First of all, I'll run my code just to make sure it's working. You know how easy it is to make mistakes in assembly. So, saying here that it's booted and it's started in 16-bit mode, which is the message I printed. So I'm going to close that now. And we're going to start to look at how we can switch into 32-bit protected mode. So what do we want to do? This is the bit we want to do here. Now, I've got some code that I've already added. So let me just put some of my functions in here, and I'm going to talk you through what these are doing. There's a few steps we need to do to switch into protected mode, and although actually there's all we actually do to make the switch is switch a flag in one of these special CPU registers. CR0 is the register name, and then we're in protected mode. But before we do that, we need to make sure we've set up some structures in memory for the CPU to configure itself. So what I'm going to include here, switch to VM. Now if I look in this include file, so remember with include files it's just a nice way to break up your assembly code. I could just paste all this in one file together, but it's nice to keep it apart. So what have I got in here then? So I've defined a function called switch to protected mode, and it does a few steps here. Now the main thing it does is it prepares the global descriptor table descriptor. Right. So this function here, LGDT, it's a CPU opcode that loads our description of the segments for protected mode into the CPU, so that when we switch into protected mode it knows how we've configured our segments. Now if you remember in one of the earlier lectures I talked about 16-bit segmentation, and I used it in examples like where I was searching, remember I was searching for strings in BIOS, so I wanted to search through as much memory as possible to see if I could find some strings in BIOS, like copyright strings or references to BIOS. And to reach up into memory I had to manipulate the segment registers. Now in 16-bit mode it works very differently to in protected mode. In 16-bit mode the segment registers, when I'm accessing memory, contain sort of an address that gets shifted by 4 bits to the left, and then the offset gets added to that to give you the absolute memory address. If you look back in the lecture you'll find I talked about that. But in protected mode what we have is it's more complex, because our segments aren't just describing like a base address in memory from where we reference with offsets. It's a more complex structure, a table that describes the protection configuration of that segment, also how big that segment is in memory, and things like if it grows up or down for a stack, the protection level for code that's running in that memory. So it's more complex, so it means that to set up protected mode, the main task that we're going to look at today is setting up this descriptor table to describe our segments to the processor, so that when we make the switch all the correct segmentation is in place for us to carry on executing code. If we don't do that, then it's all going to mess up. And another thing here, you see that I've got this instruction CLI which switches off interrupts on the CPU, because the other thing is that once I switch into protected mode, just like the segmentation completely changes, the whole architecture changes, so does the interrupt handling, which is very similar to the segmentation stuff as well. But because it all changes, it means that I've got to switch off the interrupts that are being handled by the CPU. If I don't do, and I switch into protected mode, then there will be no interrupt table set up, and it will just all die. So we've got to turn our interrupts off. So that's the first thing we do. So switch off our interrupts, then we load the global descriptor table into the CPU, which is what we're doing here. I'll go into this in a minute. And then the next step is to switch a bit of this CR0 register, which actually switches us into protected mode. So I do that here, I'm just using OR. So like with most of these registers that aren't general purpose registers, you can't just flip the bits on them, you have to shift them into some other register and then flip the bit and then put them back into the register, which is what I do here, so this should look familiar. Now, just one little thing here, a few things on here. You'll notice at the top of this file here it says bit 16, and the reason I put that in is because we're going to be mixing 16-bit and 32-bit code. Because once we switch into 32-bit protected mode, we're going to want NASIM to start outputting 32-bit opcodes rather than 16-bit opcodes. So that's what these things mean up here. So here it's saying all this code should be output as 16-bit opcodes, and this code down here, which I'll get onto, will be 32-bit opcodes. Saying that, you can still run 32-bit assembly instructions in 16-bit mode, but NASIM encodes them slightly differently. And the reason you can do that is because if you couldn't do it, then you wouldn't be able to access these other things, these other opcodes, like to switch the processor mode. So all that means is that it just changes the NASIM encoding of the opcodes to suit the configuration of the CPU. Right. So we've enabled the bit in the CRO register which switches to protected mode, and then you'll see this thing here. If you look in the, I think if you look in the Intel developer manual somewhere, it will recommend that once you've made the switch into protected mode, before you start to run any other code in protected mode, 32-bit mode, you should try and flush all the pipeline of any instructions in the CPU. This is because the CPUs are often optimized now to run things in parallel, so the instructions don't always run in order, although the outcome is the same, but you can break down the instructions into microcode and run microcode in parallel. And all it means is that if we do a long jump, which just means that if we jump to a different segment in the CPU, it will flush all of the pipeline out. So it means that after we've made the jump, we can be sure that that any instructions we run will be running in 32-bit protected mode. So this is a long jump down here. Okay, so that's how we switch into protected mode. So those are the steps. So we turn off the interrupts and the CPU, just because when we land in protected mode, the old interrupt table is not going to be used. So that thing that BIOS set up, which I'll get onto the problem with BIOS, what happened with the BIOS later. The problem is the way interrupts are handled are completely different, so we switch them off, and then we load the global descriptor table using this special instruction, LGDT, and then we switch a bit in the CR register, and that puts into protected mode, and then we do the jump just to make sure the pipeline is flushed. And when this jump lands, so you've got to see this jump here, then the first thing we need to do once we land in protected mode is to set our all of our segment registers to some valid segment that we've defined in our descriptor table, in our global descriptor table. So that's what I do down here. So I set, well, first of all I move it into AX just because I have to move it from AX into these other registers, and I just set them all up like that. Okay, so so DS, the data segment, the stack segment, the extended segment, all these general purpose segments, I just put the data segment into there that's defined in my global descriptor table, which I'll get onto. Then I set the stack as well, and then I jump into protected mode, which is, I just do this call here to a function, and this is where my bootstrapping code would pick up then to load the operating system. It will be running in 32-bit protected mode. So this is my main code for jumping into protected mode. Okay, and these are the steps we have to do. Often if you use a bootloader like Grub, for example, it can do this stuff for you, so you don't need to do this stuff, but I'm trying to show you how it works really. And so far we've not relied on any other libraries or software, so that's the goal of these lectures. Right, so where do we start now then? Well, let me just look at some, let me just show you some resources. There's lots of stuff on here now, there's lots of stuff on the web about how this stuff works. I didn't want to do that, press the wrong button. If I just look on here, Wikipedia's got a page on memory segmentation. It explains the difference between real mode segmentation and and protected mode segmentation. And what we have here is this is there's a local descriptor table and a global descriptor table. They work basically the same way, but one is for processors and one is for the global CPU. And we're using the global CPU because we've not got any idea of processors at the moment. That's like further down the line in the operating system development. So let me see if I can just find a picture of the global descriptor table. Okay, so it looks a lot like this. So what we've got is, so we're setting up these segments, and I told you that it's not just a simple, the way we define a segment, which is, think of a segment as just a block of memory that's got some bounds, like it's got a size and it's also positioned somewhere in memory, and we want to define these segments. And before we start running in 32-bit protected mode, we need at least a data segment, a code segment, and a stack segment set up, so that we can run code within those. So we have to set this up. We have to define it in our global descriptor table, and each entry of that global descriptor table defines one of these segments, and it'll tell the CPU where the segment starts in memory, where it ends in memory, what privilege levels of code it can run, stuff like that. So it looks a bit like this. So each entry is 8 bytes, and it has the base and limit. So the base is where in memory the segment starts. The limit is the size of the segment, and so it means that if the code tries to execute outside of this limit, it will throw an exception. So you can imagine boxing pieces of code into certain pieces of memory, which is what happens with processors when you come to writing a proper operating system. The thing with this structure though is that so there's the base, bits 0 to 15, and then we see that bits 24 to 31 are down here, and bits 16 to 23 are down here. It's a very strange structure, and I don't know why it splits up like these addresses in this way in structure, but it just does, and it could be some legacy hardware thing to do with the earlier CPUs. And of course, when you have a convention like that, then you can't really change it, because any code that relies on that still has to function on the new CPUs. Perhaps it's something like that, I don't know. But anyway, it's basically this 8-byte entry in this global descriptor table is describing a segment of memory, and we're going to describe segments for data, code, and the stack. Actually, what we're going to do is you can put these in different places in memory, but what we're going to do is just have a flat model, and you'll find this mentioned in the Intel Developer Manual, which is just a simple way of using the protected mode initially, which is where we take our segments and we make them the full size of memory, and we overlay them all on top of each other. So the stack segment is overlapping with the data segment, and that's overlapping with the code segment, and it just means that really there's no segregation between the code, the data, etc., which is what it's intended for, but it's just a simple memory model for us to start with, and it's easy enough to move them around. Right, this stuff as well, probably, like I said, this is probably the hardest stuff. Once you've done it, you don't need to worry about it, and I've got some code here that you can use, but it's really worth trying to understand how this stuff works, especially if you, like when you come to looking at operating system code, how it works, how it manages tasks, how it sort of structures them, and how it structures memory when you launch a process, and how memory is shared between processors, how certain protection is achieved for security in operating systems, or if you're interested in reverse engineering operating systems, then it's important to know how all this stuff works. And it's just interesting. I mean, if you're interested in the details of these things, it's just interesting to know. Right. So let's get on then. Let's go back to our code. I'm going to show you what this looks like in assembly now. So that's why this is hard, because if it was in Python or Java and you had to define those structures in memory, you would just use classes and structs or whatever. But we've got to define those initial data segments, those initial segments in assembly. Right, let's get on. There aren't so many nice examples in this lecture, but the next one will be more interesting. Right, so we've got this switch to PM, so let's go back to that code. Now, I said that we're loading the global descriptor table here, but what this instruction is doing, you'll see the bracket say, this is saying it's taking the address of this and it's loading that thing into here. But to find out what that is, we'll look in here, which is where I've put it. So I've got the GDT, the global descriptor table. Now this code here is, it looks probably more complicated than it is, and I mean it is confusing, but all it's doing is it's describing these tables. So see this table here, so each 8-byte entry which describes a segment, it's just describing all of those, but in assembly. So when I want to set a bit in memory at a particular address, then I have to do things like this. I have to declare it as like a data, you know, like when I declare a byte or something in memory, I use these data declaration instructions for the assembly. So, well, how does it work then? Well, first of all, so this is the start of the global descriptor table, and I've got this label here so I know where the start is, just like any other label. And the first entry in the global descriptor table has to be null, which just means that all the bytes in the segment are 0. And the reason that's used, I think, as I understand it, is that if you accidentally set one of your segment register to 0, then it will reference this null segment and throw an error. It'll be easy to track down the error because you know that it's not really a segment, it's a null segment. So so I suppose it's a way of defining no segment in a segment register or something like that. But anyway, we need to have this here. So if you're looking in Intel Developer Manual, it'll tell you that you need to have that there. So this DD just means declare a double word, which is 4 bytes in memory, and I do 2 of those next to each other because I want 8 bytes of zeros. Okay. So the next bit is actually an entry, and this is my code entry. So so if you look at what this is, then basically I'm just setting these values now, setting all the bytes, and in some cases I'm using this this bit notation where it's easier to define particular bits, an entry in that segment. So if we look at this thing, then I've put some comments up here to explain what they are. So for example, this code segment has got a base address of 00, so it starts at the very bottom of memory, and it's got a limit of this, which is just a big number really. So that's how many bytes are inside that segment. So that's how long it is. And the first flags, so first of all that base and that limit are set here. So limit bits 0 to 15, which are the first, if you look on here, they're the first 15 bits. Sorry, 16 bits, because 0 is included. And then the base, hang on, what's that? Yeah, so the limit, yeah, so this is the 0 bit on this side. So the limit, I declare the first 16 bits. And then the base, 0, 0, and the rest of the base is down here. I told you it's broken up strangely, it's just how it is. It doesn't really matter that it's like that, it just makes it a bit awkward to declare the addresses inside it. If you looked at, so this is equivalent, like if you look at a network packet being sent, a packet has structure, you know, it has headers, it has fields, and before it gets transmitted on the wire, they just get mapped into bytes with certain offsets within the packet. But you probably won't see network protocols that have addresses fragmented like this. You know, like if you look down here, there's how many bits is that? 32, is that 24, so 6, 7, 8 bits. So there's 8 bits of the base at the end of the structure, and there's 8 bits here, and then there's 16 bits here. Anyway, so I'm declaring my limit, declaring my base in these bytes. So I'm declaring my limit, my base in these bits. And then here are the first flags that control how the CPU treats the segment. So in the first flags, the first bit says present. I forget what all of these flags are now. You can look in the developer manual, or even you can look on here. In fact, if I look on here, present bit, this must be one. Okay, the present bit just means that if a segment is valid, it's 1. If it's not, it's 0. So it's just a way of invalidating the segment for some reason, so that the CPU won't use that. Privilege, that sets the privilege level. So 0 is actually the highest privilege level, ring 0. So it means that this is high privilege code that runs in this segment. So this, if I'm writing an operating system, then I would have high privilege code for the kernel code. And then descriptor type is another flag. So you see I set these in here. So this first bit here is the present flag. The next 2 bits are 0, which are the privilege. The next one is the descriptor type, which are these. So these parts. It's these first 4 bits, and then the next one, the next 4 bits of these first set of flags say that this is a code segment, so it means that we can run code in this segment. This is important for protection and for security, and it just tells the CPU that it's code that's stored in here, so it can distinguish between code and data if it needs to. If in 16-bit mode you just run, memory is treated as code or data, and the CPU doesn't care, which is again why it's easy to end up with security issues and stuff like that in those old operating systems. Right, the first flags, so where did we get to? So the code could form in just some flag, you could look that up. Readable, whether you can read data from it. Some segments in this protected mode you can declare them as just executable but not readable, or something like that, so that you might want to make it so that a particular region of memory can't be read as data, but it can be executed as code. And then some other things, so granularity. Granularity is just a way of extending the seg to so that have I got that on there? Yeah, so that it just means that when you declare the size of the segment, that can be multiplied by some value to become the actual size of it, to make a larger segment than the address of the limit can specify. So that's granularity. Again, you can look at these if you're interested, but what I'm showing here is that these definitions here are just setting up a particular segment that's suitable for code, and then once I've done that, I want to do something similar for data. And if we look at the differences, so we see that the data has the same limit, and it has the same base, so it overlaps the code segment, a data segment does. And then if we look at the flags, we just set them a bit slightly differently. For example, this data segment, I set the code flag to 0, so this is telling the CPU that this isn't code. Yeah, so it's I can say whether it expands up or down when we grow the segment. But that's it. So this awkward looking code here just defines my global descriptor table segment entries. And I said that I had a stack segment before, but actually I've only got a code and a data one. But I'll use the data one for the stack as well. So I've got 2 here. So this is the minimum that I need to set up if I'm going to run in protected mode. Just a code segment and a data segment. And now that I've got that, I can feed this to the CPU and then switch to protected mode, and it will know where my segments are, and I can start executing code within those segments. So how do we do that then? So first of all, we don't give the we don't just pass this address to the CPU to load it, but we set up this thing called a GDT descriptor, which is really just a reference to where my global descriptor table is in memory, and really, as far as I can see, it just serves the purpose of telling the CPU how long it is. So not only does it tell it where it is in memory, but it tells it how many entries there are inside it. So that's what we set up here. And if we look here, this is the structure of the descriptor. Yeah, so it's just got it just tells us where in memory the GDT table is that I've defined with my segments in, and it tells us it how long it is, the size of it. So so I just define the bytes like this. These things here, I'm just using the labels in NASM to calculate these values, so I don't have to type constants in. So this minus is just NASM calculating the constants. It's not executed code. So all this will do, NASM will just get the address of this in memory, the address of the start, and take the start away from the end to get the length. The size is always less 1 in the GDT, so we just put -1 on there, and then we just define the start address of our global descriptor table. Now that's all my descriptors, my segments defined now, ready for the switch into protected mode, and that's probably the most complicated. Well, it is the most complicated part, and so if you're looking at that and thinking that still doesn't make any sense, well, that's okay, and that's just have a good look at it, and cross-reference it with the Intel developer manual, and also maybe some easily digestible stuff like the wiki pages, like OSDev and stuff like that. So if I go back to my code and look at what I've got, I'm going to look at this again just to keep reeling it in. So I include my GDT there, and you'll see that this label here, GDT descriptor, is just the label for the address of where my descriptor is for the GDT, which tells the CPU where the GDT is. So there's the GDT, the actual table defining my segments, and then there's the GDT descriptor, which sort of tells the CPU where the actual GDT table is and how long it is. So it's the address of that I pass into LGDT. So now the CPU knows about my segments that I just defined. It knows that I've got two segments, a code segment, a data segment, and they overlap each other. So that's good. And then I switch this flag to switch into protected mode, and then I do this jump into protected mode. These instructions here are 32-bit instructions. So so that's why I've got 32-bit there, because this code gets reached after we've switched into protected mode. I mentioned this before, I'm just going over it again because now we've looked at the GDT and it might make more sense what some of these things are. So this data seg here, what this actually is this value is the index into that GDT. So data seg, if I go to if I jump to it, I didn't mention down here at the bottom that I calculated these. So the way once we're accessing segments, so when we switch in segments in our code to move into different areas of memory in protected mode, we use the index of the actual segment entry in the table to tell the CPU which one we want. So the CPU knows about this table now because I've loaded it in, so it knows about GDT code and GDT data, but it's just a table. And if we want to load the code segment into one of the segment registers, then I use the index of this, and in this case it's going to be, if this is index 0, then this is going to be index 1, and the data segment is going to be index 2. And I can just get NASM to calculate those by using my label, just doing a label calculation. So I've got GDT code minus the start, it will just give me the address, it will give me the index of the code segment, and the same for the data segment. So they just point to indexes in the table, and that's what we're moving to here. So what I'm doing here is I'm saying all of these general purpose registers, DS, SS, well, stack segment is not general purpose, but all of these segments we're moving the data segment into. We're saying, so for example, when we're operating on our stack, by default, unless we specify a particular segment address, then our stack will operate on the SS segment. So we move the data segment into there. Then we readjust our stack, just like we always do, just to make sure that it's in a safe position. And then we call this begin PM, which is in my main code, which is just where we take over for our loading our operating system. So so that's everything really. So some more things to look at here then. When I've got this jump here, I said we had a far jump, and by a far jump, a far jump is just a jump that jumps into a different segment. So all we do here is we explicitly say jump to this address in memory, but switch the code segment. Switch the segment, the memory segment, to code seg, which is the index of our code segment in our global descriptor table. So because we explicitly say this segment, it's a far jump, so the CPU will flush the buffers. Really, this is, apart from the fact that it flushes the buffers, what we're doing is this. That's what we're achieving. So when I say far jump, it doesn't mean very far in memory. It just means it's far because the segment is, we're changing the segment. Okay. So yeah, because once we've switched into protected mode here, although we've defined those segments, they're not being used anywhere. We've not set them to use anywhere. So that's why we're doing this jump, this far jump, and it will switch us into the code segment. And then once we're in there, we can set up the other segments for data. Okay. So let's have a look at this. So what I'm going to do is so switcher and PM. So I've got this function. So I'm printing my string, and I've included those files now, so I've got that stuff there, how to switch into protected mode, but I just need to use it now, so using a call, so I'm going to do so call, and then my function was called switch to PM. So this should switch them into protected mode. I should get an error now, let's just see. Yes, Nazim saying there's no begin PM, which means that we've not defined our label for where to jump to after we've switched into protected mode. So let's just put this down here then. Begin PM. Let's hang at the end of here. So if you're writing some code, think of this as the main method for where I've just entered protected mode. So I've done the switch and I'm going to land here. So let's see what happens. Okay, so well, we see the same thing as before. The problem, as ever with low-level development like this, is that you don't get much feedback. So we need to probably print out a message. The machine didn't crash, and it would be easy to do that by misconfiguring one of those settings. Or I've not tried this, but let's try, for example, if we in our switch to protected mode, let's say that we forgot to disable the interrupts. Let's just see if anything happens. It might not do, but it's good to play around with these things. Oh yeah, there we go. Oh dear. Yeah, so what's happening? Well, it looks like the machine emulator is just rebooting itself over and over. So it shows you that I need to follow those steps, otherwise things go wrong. So I commented out the clear interrupts instruction, so it means that I switched into protected mode, but I left the interrupt stuff enabled in the CPU. So what would have happened was, when I switched into protected mode, some interrupts would have been firing from hardware or from a timer or something like that. And because we're switching to protected mode, but we've not yet set up the interrupt table, which is completely different in protected mode to it was in real mode, which is a very simple table, then it doesn't, well, when an interrupt fires, it's undefined, it doesn't know, there's no handler set up for it, it doesn't know where to go to. So that's where I have to disable them. And we'll disable the interrupts until we set up our interrupt table. But I'll leave that for you later on, because that's something that, that's another lecture series probably. If you read the developer manual, you can figure it out how to do it. But you need to make sure that everything's ready for you to switch over. So let's put those interrupts back on. Sorry, let's enable that command to disable interrupts. Right. So what else have we got in here? Let's see. Okay, so we're back working again now. So we switched into protected mode. So what we want to do now is print a message. We're going to print that protected mode started. Now I had my my print function, so let's just do something similar down here. So we want to show that we've landed in protected mode without anything crashing. Now another mistake I've made here is that I need to remember to tell my my NASM that this code here, the instructions in here, are 32-bit instructions, and I'll put 16-bit back again down here. One thing I didn't mention actually, which is I've only really used it, well, let's say here, so EBP. So we know that we had a pointer called base pointer for the stack, and we've set that before, but you see here I've got EBP, and once I'm in 32-bit mode, well, once I'm using 32-bit opcodes in 32-bit mode, I've got wider registers, so I can reference 32-bit registers, and all it does is you just put an E on the front of the register name, and that will give you access to the full 32-bit value in the register. Apart from that, it works just the same as before. You can still access these access them as 16-bit registers too, which is just setting and getting data from the lower 16 bits. But this is 32-bit code now, and this is the sort of code that your compiler will generate when we start to compile some C code in the next lecture. So we're in 32-bit mode then. Okay, what was I talking about? So switch to PM mode. So we switch to PM mode. Let's print a message, and let's print out a message that says that we've landed in protected mode, and then we'll know that it's all working. Uh-oh. Okay, so, well, what's gone wrong? It's the computer's rebooting itself again. So it sounds like something similar to last time. Let's have a look at the code. So what did I do? I've landed in protected mode, and it seemed to be working fine, other than I didn't see anything. But then when I tried to print a message, it all went wrong. Well, if we look at this print string function, well, first of all, you'll see that we've looked at this function in one of the earlier lectures, how to write a function that prints to the screen. And this function here, excuse me, this function is using BIOS to print a character to the screen, using the scrolling teletype routines in BIOS that we talked about before. But there's one reality now that we've got to get used to, and that's that once we're in protected mode, BIOS is useless. So all of the stuff that BIOS offers us for accessing the disk and for printing and stuff like that is all 16-bit code, and it's all loaded for the initial 16-bit real mode of the CPU. And before, I sort of hinted at that really, because I showed you that when we left the interrupts enabled, it all messed up because the interrupt table is completely different. Interrupt handling is completely different in protected mode than it is in real mode. So BIOS, when it loaded, it set up that interrupt table for allowing us to use devices, and now that's not usable anymore. So nothing that BIOS does that relies on interrupts is usable. in protected mode, and probably a lot of the other code isn't either, that relies on 16-bit operation, like 16-bit segments and stuff. So BIOS is no more. So that's one of the downsides of going into 32-bit mode. But the point is that BIOS is really just there to get us started, which is what it did, and the computer is much more powerful than it is when it's running in an old 16-bit real mode, when it's in a protected mode. So so we can't call our print string function, so we can't print a message like this. But what we can do is, most CPUs when they start, and in fact what BIOS would have done when it set up the video driver for us, it would have set it up in some sort of compatibility mode, VGA mode, and it would have mapped the memory of the video device somewhere into memory, so that what BIOS is actually doing when we print to the screen is it's writing bytes to that memory that then display characters on the screen. And so it means that without BIOS we can just sort of bypass what BIOS was doing and just write the characters to the screen directly. We just need to know where they are, but the good thing is that they're always in a consistent place in memory. So we need a new print string function. What I'm going to do is just, before I do this, I'll just get my, I'll just have a go at something. I want to show you, if I get this right, is that I should be able to, if I move something to memory, so if I do, well first of all, video memory is at this address. I'll just make a note. So video memory for our standard VGA mode is at this address. Okay, and what that means is that if I write a character to that address, then it should put the character at the top left of the screen, and the next character will be not the next byte after that, but the byte after that. And the way you can find stuff like this probably on the web as well, but the way the screen works is that you can view the screen, the character mode of the screen, as just an array of bytes, and each byte holds a character. So there's two bytes next to each other. One byte tells the screen which character to display, and the other byte tells it some properties like the colour of the character to display. So by setting those, we can write a print function that prints to the screen. It is direct to this address in memory. So let's just try that. So if I do, well first of all let's use, so if I do store this address into this register, and then if I do move edx, I have to tell it that I'm moving a byte, because otherwise it doesn't know how to write to that, because there's no size for that. This is just an address, so when I put brackets edx, it's just saying write to this address. So I tell it I want to write a byte to that address, and the byte I want to write is an A. So let's see now. So this is the address in memory that maps to the VGA display, character display, and I'm just writing the character A, or the byte, the ASCII byte for that character, to this address. It should print it on the screen. Let's have a look. Yeah, there it is. So it's just, that's our A there. If I do, I'll show you how they're structured then. So the byte next to the byte for the character is the it's like the properties of that character, how to display it, the colour. So there's 8 bits used for colour. If I do, we can show that by just doing, if I do a B to the next character, to the next address in video memory, then it didn't print a B, but it's changed my A into a green A on a red background. So what I wanted to do actually to print a B next to that is close that down and print to the byte 1 after that one, which is the next character to display. So now I've got an A and a B. So now I'm printed to the screen without BIOS. I'm just writing directly to video memory to display it to the screen. And now, if I just get rid of this now, because I've got some code already. So if I include what's it called? So if I include my, I just called it my PM functions, my functions for protected mode. So I've included those now, and in there I've got a nice function for printing strings in protected mode. If I look at that, all it does is it's very similar to the one that used BIOS interrupts to print characters. And instead of calling interrupt to print the character, it places it at a particular offset in memory address. So it's very similar. You can look at that. You should be able to figure it out based on the other ones we did. And also I've just set this constant white on black, which is this. If I set the byte to this, just to F, then it gives me white on black. So it sets a white text on a black background. So and the way I use that function, just like my real mode function, I move the address of what I want to print into the ESI function register, and I want to print this message protected mode, and then I do a call print string PM. Ah, there we go. Well, what do you think about that then? Like some of the other stuff we've looked at. So what that's showing now is that we switch into 32-bit protected mode and we're printing a string to the screen. If we would have messed up somewhere, it's very likely that we wouldn't have got that far. It would have just bombed out. So we managed to set up the CPU all ready for protected mode. Yeah, and like I said in the other things, if you told somebody that you could print a string to the screen like that, then they probably wouldn't appreciate it if they'd not gone through the process of understanding how the computer works. But you've got no support from software. There's only BIOS, and even BIOS is gone now. So you really get to understand how the computer works, and using little examples like this, playing with the emulator, looking at the online resources, and looking at the Intel developer manual, you should be able to really start to learn about this stuff if you want to. So that's good. So let me just quickly summarise what we did to do that as quickly as I can. So first of all, we printed a message in real mode to say that we started in real mode, and then we called this function switch to protected mode, which we defined, that did this. So that function, it just cleared the interrupts. Remember, if we left interrupts on, it caused all sorts of havoc once we switched over. And then it loaded the global descriptor table. Basically it's telling the CPU, here's how I want my segments configured for protected mode, and I define the structures there, which are these structures in here. And you can get more details from the Intel developer manual. And once it had loaded the descriptor table, it switched into protected mode by flipping that bit in the special register CR0, and then it did the long jump into our 32-bit code to start, just to initialize the rest of the state of the CPU ready to start running some code, some custom code to boot an operating system or something. So we did this far jump here just to flush the pipeline to make sure that the CPU didn't have any half-finished microcode executing. And then we set up the stack, we set up our segments, because until we set up these segments here, they'll all be undefined, and if we ever try and use them in our code without setting them up, then strange things will happen. They'll still have values in possibly from when we're in real mode that won't make sense in protected mode, so we've got to make sure they're all set up. And then once we've done that, we jump into our protected mode section here, and all I do is print a message then. And to print the message, I can't use BIOS because BIOS is no longer there. It's no longer, it doesn't make sense anymore once we're in protected mode. Then we use our print string function to print directly to display memory, video memory, to print out a string. And that's it really. So we switched to protected mode, and now in the next lecture we're going to look at, which is the last lecture in this series, we're going to look at compiling some C code to make a very little tiny kernel of C code that we can then, you can imagine building that up then. Once you get the abstraction of C, then it's much faster to work for defining things like structures like we did there. We can define the interrupt table in C if we want to, and then switch our interrupts back on, and then if we want to we can start writing simple device drivers in C code. So there we go. So thank you very much, and thank you for your patience. It's yeah, this is probably the hardest bit, and I mean, I find it quite hard to explain it. There's probably a lot of content there that it covers that if you just go away and have a look at it, you should start to become more familiar with it, and hopefully the introduction I gave you should help you to find your way around that. Okay, thank you.